Hello, welcome to another brief video lesson on stars, magnitudes, absolute, and apparent. This class will focus on a basic understanding of stellar magnitudes. What is a magnitude? It's how bright an object is. And there are two ways of viewing it. There's an absolute magnitude and there's an apparent magnitude. We're going to talk about both of these. These are absolutely fundamental to understanding stars, double stars, variable stars, and what have you. This is key. So having said that, this video may run a few minutes longer because the fundamental concept is so important to what you're doing in your astronomical studies. All right, brightness, where it all begins. Basically, it all begins from the source. It begins from the stars. They have their own internal fusion, and they generate an inherent luminosity. So a luminosity is how much power this star has, where it's having its fusion take place. So wherever it is in space, its power output is its luminosity. The luminosity then spreads out through space, and that's what we're seeing here. It starts at the light source, but it goes out a particular distance, however far, in the case of us, from the origin of the star to us, that distance, but this light spreads out. The light that we ultimately measure when it arrives to us is something that we know is flux. So we have two key terms here. We have luminosity and we have flux. Luminosity is the power output of the star at its source. Flux is what we can measure in our detectors, in our CCD cameras, through our telescopes. It's what we get here. So let's talk about the inverse square law of brightness. As light moves away from a point source, in this case the star, it gets diluted over time, over distance. It spreads out over progressively larger areas. So if you think of this light source here, this is a sphere, and this thing is fluxing, and it's with its fusion inside, it's generating all this luminosity, but it's emanating it into space. And so this emanation becomes larger and larger as this goes out. And as it's this same amount of light spreads, that's where we get the decrease in brightness over distance. So the amount of radiation received by the detector at our end, flux, varies inversely as the square of the distance from the source. So what we have here is the apparent brightness. Now, apparent means what you see. Go out tonight in the night sky, look at the stars. How bright they are to you is the apparent brightness, what it appears to you. It's important that you understand what apparent means. So the apparent brightness is proportional to the luminosity at the source divided by the distance square. The more distant a particular star is, the fainter it will appear to you. Its flux, what we see, which is kind of its apparent brightness here, is the luminosity over the distance squared, but we then add the terms for the sphere which it is emanating from. So an apparent magnitude, let's look at the two stars on the right against the background. We have the A star and we have the B star, and they both appear to have different brightnesses. In this case, B appears brighter than A. That's all we know at this point. It just appears brighter. It doesn't tell us anything about the luminosity at the source. It just tells us about what it appears to you. So for example, the A could be the most massive star ever created in the universe, but it is so far away, it appears very dim to us. And the B star could be the weakest, faintest little star, but it's right next to us, therefore it appears very bright. So from the apparent brightness, you really can't tell what the ultimate brightness is going to be. So how do we measure apparent brightness? We do it in a magnitude scale, and it's kind of a strange scale. This was derived from the ancient Greeks, from Hipparchus, and he measured, based on visible stars, that's all they had at the time, a range of brightnesses. And they start out with the most bright being magnitude of 1. And the faintest that you went was 6. That's as far as the visible eye can see. So it's a strange scale in the sense that the larger the positive number, the fainter it is. So if we take a magnitude of 30, it's a very, very, very faint star. If you go to a magnitude of minus 26, like the sun, it's a very, very bright star. We'll see that in just a second. So this absolute scale was derived from the Greeks. 1 is bright, the larger number 6 is significantly fainter. This is a logarithmic scale. So each derivation, 1, 2, 3, if you have this to the power of 2.512, you get the next value in the logarithmic scale. These 5 branches are broken down as such. The magnitude scale, as we mentioned here, minus 26.8 is the sun. If we take these negative values that you see here and we come all the way down to the positive, we get down to plus 30, the faintest object that the Hubble Space Telescope is able to see. We, at a plus 6, that is the best your naked eye can do in an absolutely dark sky. Within this range here, we have everything that is visible to us, from the moon to the planets to the faintest star that the eye can see. Beyond that, the higher values beyond here require the use of a telescope. Your key takeaway here is negative values of magnitude are very bright, positive values of magnitude are very dim. It's kind of a messed up scale, but that's what we have. All right, let's move from apparent to absolute. As I said earlier, apparent is what you see. What does it tell us about the star? Not much. Just tells me what I see, what I can measure, the flux. So scientists derived a yardstick, and they call this the absolute magnitude. This absolute magnitude is tied to luminosity. Now remember, luminosity is what I said is at the source. What is the star doing where it exists? That's luminosity. So this yardstick, to make all of these stars equal, is at 10 parsecs. 10 parsecs was derived as an arbitrary distance to place all stars. Now, if I could take every star in space and I could put it at 10 parsecs, then the magnitude that we measure from that really tells us something, because the distance is neutralized. It's all the same distance apart. In an earlier video, you may have remembered that we talked about these central stars in the Orion's belt. What you have listed here, 2.0, 1.7, 2.2, those are the apparent magnitudes. Well, that's what our eye sees. They're relatively the same. But as we talked about, the distance to the center one here when we use parsecs, Alniam is much further away. So if it's the same brightness in my apparent eye, but it's further away, I know that its absolute magnitude must be much greater, because the more distant an object, the dimmer it is. But yet this thing is pretty darn bright. So apparent magnitude is what I see. Absolute magnitude is at a distance of 10 parsecs. And it actually tells me something about the luminosity of the star, because they're all at 10 parsecs on this scale. That's the difference between absolute and apparent magnitude. So let's look at a couple of examples here. We have Sirius and Rigel. Sirius is the brightest star in the night sky. Absent the planets, is the brightest thing you will see. Rigel is the brightest star we have in the Orion constellation. So here are their distances. Their parsec differences are significantly different. Rigel is much further away, 240 parsecs away. Sirius is right next door, 2.7 parsecs is very, very close to us. So the apparent magnitude is such, the apparent, remember what I see, is Sirius is much brighter. It's at a negative magnitude value. It's a very bright star. Rigel is right about 0 magnitude from an apparent scale. Fortunately, these two are in the same part of the night sky, and you can see this in the winter. Now, if I take the absolute magnitude and I put them at that 10 parsec distance, things significantly flip. So both of these stars put at 10 parsecs away. Now what's the magnitude? Sirius becomes dimmer. Remember, positive values of magnitude are dimmer stars. It's +1. Rigel becomes very bright. It's at a -6. Remember, negative numbers are bright on the magnitude scale. So notice how these numbers flipped. Apparent magnitude doesn't tell us much. Absolute tells us a lot, because now they're on the same yard scale or yardstick. They're 10 parsecs away. From this, we can use the distance modulus. This is where the apparent and the absolute really come to play with each other. So apparent magnitude is always discussed as a lowercase m. The absolute magnitude is a capital M. If both of these are known, and we can do this because apparent we can get from the flux Absolute magnitude you can get from catalogs or from stellar spectra. You can determine the distance to a star. Conversely, if you know the distance and you don't know one of the others, you can derive the other. And the equation is simple. It's here. This is known as the distance modulus. The absolute magnitude subtracted by the apparent magnitude equals -5 times the log of the distance plus 5. That means if you know the distance of the star, you can obtain any of the others. Or if you don't know the distance, but you know the magnitudes, you can manipulate the formula to get what you need. The distance modulus is key to our understanding of spectral qualities. So in summary, we've thrown a lot at you today. I want to talk about a couple of terms. Remember, luminosity. This is the output of the star at its source. This is where it is and where it's fusing and the energy that's coming off of this. The flux is what we see when it reaches our detector. So the difference is the power output there versus what I see here. The inverse square law of brightness discusses this difference. Basically, the further something away is, the fainter it becomes. It's nothing to do with this luminosity, its total power. It's just what I see is less because of how far this thing is away. The apparent magnitude is what I see on the night sky. The absolute magnitude is how bright all stars are at a distance of 10 parsecs. So these are all key terms that we'll discuss. Thank you for your attention. I know this has been a longer video, but this is extremely important in the understanding of stellar properties. We look forward to seeing you on another brief video lesson.